Hello, everyone. I am Tony Zhang from the University of Michigan. In this talk, I will introduce the new concept of invariant taxonomies. The goal is to simplify the task of formally proving distributed protocols, hopefully in a way that sparks joy in the user. This is joint work with Hance, Manos, Kapritsos, Chajed, and Bryan, Parno. So as this cartoon depicts, distributed systems are notoriously difficult to design correctly. This is due to their scale and their need to handle all kinds of non-determinism, such as server failures and asynchronous networks. Importantly, such systems underpin critical computing infrastructure, and hence any failures in these systems can have severe consequences. To address this concern, researchers and practitioners have embraced a powerful approach, that is formal verification. Formal methods are great because they rigorously prove the correctness of the system to categorically eliminate bugs at compile time. So let's see how this is done. In verifying a distributed protocol, the goal is to show that a safety property P is an invariant. For example, in a consensus protocol, a safety property could be that all nodes reaching a decision agree on the same value. Proving a safety property in a distributed protocol generally requires 3 steps. First, we model our system as a state machine. Each global state includes the state of the network and the states of a collection of hosts. Second, we want to find an inductive invariant, I, for the system. I is a strengthening of P that is closed under transitions, and it is typically expressed as a conjunct of many smaller invariants. So as a quick 30-second refresh, let me give some background on why we need this inductive invariant. Why is this safety property P alone not enough? So to answer this, we can view the states of a system as a Venn diagram. In this set, we have a subset of reachable states of the system. We also have a set of safe states that satisfy our safety property P, beyond which are unsafe states. Generally, P is not inductive, meaning that there exist states satisfying P that can transition to unsafe states. Hence, we need to find an inductive strengthening of P called the inductive invariant. This invariant I must be weak enough to encompass all the reachable states and be strong enough such that the states satisfying I can only transition to states that also satisfy I. So finally, after identifying this inductive invariant, we can then write an inductive proof to show that this I is indeed correct. These last 2 steps are really hard. Even simple protocols have a long list of conjuncts in their inductive invariants. Deriving each of them manually requires deep user expertise. Finally, proving its correctness is also a labor-intensive task. The reason for this difficulty is that in general, finding and proving inductive invariants is undecidable. The user must manually supply these invariants and proofs to guide the verifier. Note that there is the alternative of using only decidable logic, which then unlocks automated invariant finding. However, decidable logic has very limited expressivity. For instance, it doesn't permit common structures that developers use, such as arithmetic. These techniques hence require the user to perform creative abstractions to fit their protocol within decidable logic. So in this work, we focus on the general undecidable setting, where developers can express their protocols more naturally. The goal is to reduce developer burden in a way that sparks joy in the heart of the user. We achieve this by first identifying patterns that let us derive and prove many invariants automatically. These patterns are what we call the invariant taxonomy. We then develop the Condo tool that lets developers prove a simplified version of the protocol. Condo then uses the automation afforded by the taxonomy to lift this simpler proof to the full protocol. So the rest of this talk has 3 parts. First, we identify ways in which finding invariants is hard. And for the purpose of this talk, I will focus on the network aspect of the problem. Then, I'll show you the key insight of this work, which is that there are recurring patterns that we can use to simplify this problem, and we organize them in the invariant taxonomy. Finally, I'll introduce our tool, Condo, to leverage the taxonomy. It lets users focus on fewer key invariants that warrant their effort while automating the rest. So let's start in part 1. In distributed protocols, the network is actually something that adds clutter and complexity to reasoning about inductive invariants. So to see this, let's study the very simple two-phase commit protocol. In this system, nodes agree to abort or commit a transaction depending on the preference of participants. So first, the leader collects participant preferences through votes. The leader decides to commit if all votes are yes, else it decides abort. It then sends the decision to participants who follow that decision. The safety property we want to prove is, if any participant reaches a commit decision, then everyone's local preference must be yes. Now let's try to write an inductive invariant to actually prove this property. So recall that the inductive invariant I is a conjunct of many smaller protocol properties. One such property is the following. If a participant's local decision is commit, then the leader's decision must also be the same. Now this is where the network starts to make reasoning complicated. I0 on its own is not inductive, as there is no direct coupling between leader and participant states. Instead, when the participant makes its decision, it does so by observing a message in the network. And it is then the network state that implies facts about the leader state. Hence, to actually prove I0, the user must come up with additional supporting invariants about the network. So namely, we need another invariant I1 to say that if the participant decided commit, then there is a commit message in the network. We also need I2 to say that if there is such a message, then the leader decided commit. It is then the conjunction of these three invariants that is inductive. And prior to this work, it was the responsibility of the user to come up with them. And so this puts a lot of burden on the user. The way these network properties show up is actually a recurring pattern. The property that we want to prove is usually some relationship between host states. There are interesting properties that captures why this protocol is correct. However, to actually complete the proof, we have to add extra assertions about the network. These network properties are pedantic. They serve the pedantic role of ensuring that the host property we actually care about is inductive. So now imagine then, won't it be nice if we don't have to think about the network at all? What if as a user, I only need to think about invariants that deal with host states, like I0, and not all these pedantic network properties? I can then prove the protocol as if the network did not exist. So our work makes this vision a reality. I now show how we free the user from worrying about pedantic invariants, such as these network properties. Our key insight is that these less interesting properties are actually mechanical, and they all follow similar patterns. So let's examine what we've been doing. The property that we want to prove is usually some relationship between hosts. How the state of some recipient implies facts about the state of some sender. However, the network introduces a logical indirection. We have to first reason about what the receiver implies about the network, and in turn, what the resulting network says about the sender. And this pattern is actually repeated across a ton of host invariants that we write. This brings us to our insight. In every protocol, the network is simply a standard medium of communication. It only serves to convey information and does not actually contribute to the logic of the protocol. In other words, given some network semantics, the network affects every host property in the same way. And by studying these patterns, we can derive network properties mechanically. One pattern for deriving them is as follows. Every existence of a message of type T tells us that the source host performed the action that sent the message. Call this action AT. This, in turn, informs us about the state of the sender as dictated by the conditions listed in that action. And overall, we can derive properties about the protocol just from examining individual protocol actions. As a concrete example, consider the leader host in two-phase commit. Suppose there's a commit message in the network. Then, by the existence of that message, it must be true that at some point in the past, the host ran a step that sent the message. This action also sets the local decision to commit, and hence we know the decision at v prime is commit. Finally, by proving that the local decision is always monotonic, we know that the current decision value must also be commit. As such, we obtain the following network property that is true in all states in any execution. Namely, if there's a commit message in the network, then the current decision at the leader must reflect that. These network properties, which we call message invariants, is just one instance of recurring patterns that generalize into the invariant taxonomy. Other categories like monotonicity and ownership are described in the full paper. The taxonomy factors invariants into two main tiers. The lower tier of regular invariants have simple structure. They concern low-level properties that follow from network semantics and the syntactic structure of protocol steps. They are hence easy to derive and prove. Then there is the higher class of protocol invariants that deal with the global relationship between hosts. These capture the logic of the particular protocol and thus may require more careful developer thought. I now introduce our tool, Condo, that uses this taxonomy to help automate proofs. Using Condo, protocol invariants are what the user spent their time on. Meanwhile, regular invariants are made transparent to the user and handled through automation. As such, the user only focuses on protocol invariants. Notice how these invariants only refer to host states and don't mention the network. For example, the participant and leader agreeing on their decision values was a protocol invariant in two-phase commit. So, with the network out of the picture, it is possible to reason about invariants in a much simpler version of a given protocol. This version is one in which messages are delivered instantaneously between hosts. A sender sending a message and the receiver receiving it occurs as one atomic step without a network delay. And we call this the synchronous version of the protocol. So with this observation, we describe what our new user workflow looks like. In Condo, users are only concerned with protocol invariants that deal with host states and ignore the network. As we discussed, this often constitutes a proof of the synchronous version of the protocol. Then, from just thinking about this synchronous protocol and waving a magic wand, the user obtains a final proof that the full asynchronous protocol is correct. And we implement this magic wand as Condo. In Condo, the user begins by stating and proving the synchronous version of the protocol. Then the automation steps in. Condo generates the asynchronous protocol and finds and proves regular invariants with a tiny bit of user guidance. By merging the synchronous proof from step 2 with the regular invariants from step 4, we get a draft proof that's very close to the final proof. Sometimes this draft proof itself passes the verifier, and in that case, we're done. That's the final proof. Otherwise, the user steps in to fill in small gaps in the proof. Ultimately, the result is a proof showing that the full asynchronous protocol is correct. So here's a sample of the protocols on which we evaluated Condo. These graphs show the number of invariants a developer have to manually find without using Condo. And we see that the effort becomes much less when they use Condo. We see a reduction from 8 to 4 in two-phase commit, for instance. Next, the bottom graph counts the lines of Daphne proof code that the user writes. So with the help of Condo, this effort is again reduced. For instance, there's a 60% drop in echo server to a 20% drop in two-phase commit. Overall, Condo lets the user write simpler invariants and smaller proofs, basically for free, just by applying this magic wand of Condo. In conclusion, finding and proving invariants is hard in this general undecidable setting. Our insight is that a lot of the difficulties are actually recurring patterns in distributed systems. We introduce the invariant taxonomy to factor invariants into standard categories. It then becomes easy to derive and prove many of these properties. Finally, we developed the Condo tool to leverage this taxonomy. In Condo, users prove a simpler synchronous version of the protocol. Condo then aids the user in lifting it to the asynchronous setting. Importantly, Condo targets general verification frameworks such as Daphne, and has no restrictions on the logic that developers can use to express their protocols. With that, thank you for your attention, and I'm happy to take questions.